This is the last video in our series explaining the magnitude of centripetal acceleration for uniform circular motion, and part 2 of the proof. In this video, we're going to derive the expression for the acceleration vector. We'll derive this from the velocity vector that we derived in the last video. The velocity vector, the x component of it, is the magnitude of the velocity, some magnitude, times negative the y coordinate divided by the radius of the circle. And similarly for the y component of the vector except with the x coordinate. The cool thing is when we take the derivative of these expressions with respect to time, or the angle of the circle, which amount to the same thing, the only parts of this equation that are changing are the x and y coordinates. The reason is that v is constant because this is uniform circular motion. So we get this expression here for the acceleration vector. Now we have a cool final step. The rate at which the y-coordinate is changing with respect to theta is just the y component of the velocity vector. And similarly, the rate at which the x component is changing with respect to theta is the x component of the velocity vector. And so this expression you see here is a valid expression for the acceleration vector of a particle in uniform circular motion. However, we can go one step further to really see the magnitude of this vector. Note from the last video and from trigonometry that x over r is just the cosine of theta and y over r is just the sine of theta. And I hope it's pretty easy to see that when you take the magnitude of this vector, because cosine squared plus sine squared equals 1, those will kind of go away and you'll be left with the magnitude of v squared over r as the final expression for the magnitude of this acceleration vector.